This will be our second video on modern physics and particularly quantum physics. And I will hope in this video we will solve some questions. I should say more questions than in the last video, because last video was mostly the conceptual video. So here we will look at Compton effect. And although Einstein's photon model provided an explanation for photoelectric effect, many physicists remained skeptical about Einstein's discovery. So the wave model of light was so successful at explaining most of the known properties of the light, it still seemed reasonable to expect that some explanation of the photoelectric effect would be questioned. So in 1923, Compton had an experiment that provided a clear explanation or example of the particle nature of the light, and finally convinced most physicists who still doubted in Einstein's photon model. So Compton noticed that the electrons scattered when they traveled and would be blocked by the graphite. So he observed this scattering is happening in all different directions. This observation, Compton's observation, is now called Compton's scattering, and it explains the change in wavelength of the scattered X-ray photons, and is called Compton's effect. So what Compton did is he used the rest energy formula that Einstein provided, mc squared, and he turned it into the momentum formula. So what he did is, because the waves, the light waves, can be both light waves and or the light can be both waves and particle. So what he did, he said mc squared. So he did mc squared. He rewrote it, so when the photon bombards the electron, so on the right, the picture, then later on the electron can be scattered and the photon of different light can be reflected. So he rewrote it as the mass of the electron that is scattered and its velocity times the speed of light. And then the part where you see mv becomes it's now called the momentum of the X-ray. So you have the momentum of the X-ray in times the speed of light. This energy comes from the energy of the photon, which is Planck's constant times the frequency of that photon. So from here, if I use this part of the formula, I can calculate the momentum of the X-ray is going to be equal to the Planck's constant, the frequency of the photon, divided by the speed of light. And I can also rewrite it as the Planck's constant divided by c over the frequency. And then c over the frequency gives me the wavelength. So here I have the Planck's constant over the wavelength. And when I say the wavelength, that is the wavelength of the X-ray. So quickly to go over this, just to finalize what the Compton's effect is about. So when the photon enters the matter, it is likely to interact with the atomic electrons, and the photon is scattered from only one electron rather than from all the electrons in the material. When I have the photon entering the material and meeting an electron, so here is an electron, and photon energy is equal to Planck's constant in the frequency of the photon. This electron can be knocked out from its orbit, so the electron can leave the orbit and will have some momentum. And at the same time, there's going to be another photon, lower energy than the original one, leaving and having the momentum of the photon, which is the energy of the photon over the speed of light. And then this is where we have the energy of this photon is equal to the Planck's constant divided by the wavelength of this new photon. Here is one more conceptual part, and since light seems to have both wave and particle properties, or dual properties, it is natural to ask the question, so the matter, electrons and photons, might also have both wave and particle characteristics. So there were many scientists, including Louis de Broglie, the French scientist, also at the beginning of 1900s, at the same time when Einstein and Compton were learning and studying the quality of the light. So Louis de Broglie, the formula, the Compton that we just derived over there, as the wavelength, and he said that electrons can have the wavelength determined from the Planck's constant divided by the momentum of those electrons. So you have the Planck's constant divided by the mass times velocity of those scattered electrons. So the main reason why this formula is going to be important and we're going to be looking at is because de Broglie suggested that the particles can exhibit properties of waves. And so if an electron has a velocity, the double slit experiment, that electron can behave as a wave. We can represent an electron's wave length, if it was a light or a photon, using de Broglie's formula. So here's going to be our first question, and it says, calculate the maximum kinetic energy of the electrons ejected from this tungsten surface. So every material has the work energy, the energy needed to pull out electron from its surface by ultraviolet radiation. So they give you the frequency of the coming photons, 1.45 10 to the 15 hertz. If tungsten surface has the wavelength of 272 nanometers, and when they say tungsten surface has the wavelength, that means I can use this wavelength to find the energy needed to pull out the electrons from tungsten. So they ask maximum kinetic energy electrons will have after they are ejected. So you know that the energy of the photon is h times the frequency of the photon, and that is equal to the work energy plus the kinetic energy of the electron that's being ejected. So the frequency of the photon is given. So they ask me to find an answer in electron volts. So I have to plug in my Planck's constant in electron volts. At first, I'm going to rewrite equations with all the known variables that they give me. So I have the photon energy equals to, and then they give me the work energy I can find using Compton's formula. So I have the Planck's constant times the speed of light divided by the wavelength of the material tungsten that they give you, and wherever is left is going to be the kinetic energy of the electron. So that's going to be the kinetic energy of the electrons that are ejected, and we are looking for the maximum kinetic energy, so we're looking for that kinetic energy part. So because they ask me electron volts, so I have to plug in my Planck's constant in electron volts, which is 414 10 to the negative 15. Then for the energy of the incoming photons, it's an ultraviolet radiation, and they give you the frequency, which is 1.45 10 to the positive 15, and then equals to, again, I have another Planck's constant has to stay in electron volts because I need my answer in electron volts, so negative 15, and then I have the speed of light, 310 to the 8 meters per second, and then divide by the wavelength that they give me, which is 272, and it's nanometer, and nano means negative 9, and then wherever's left is going to be the kinetic energy of the electron being ejected. Now if I plug in my numbers, this is what I get. So negative 15 and positive 15 cancels. If I multiply 414 and 145, I will get 6, and then on the other side, if I simplify that, I will have, it will be 446, 457, and plus the kinetic energy of the electron, and that's going to be the maximum kinetic energy, and that's the one that we're looking for. So the maximum kinetic energy of the electrons ejected will be equal from tungsten will be equal to 1.43 electron volts. If they ask you to convert electron volts into joules, you plug in electron charge, so you would have 143 times 1.6, 10 to the negative 19, and that will be in joules. So in this question, the next one, they're saying that calculate the wavelength of the emitted photon for the electron which jumped from the first excited state to the ground and emitted the single photon with energy of 6 electron volts. So you have different states where the electron can be, and eventually there's going to be like the ground level, so the 0. The last state is where the electron is the most excited electron, and after the state the electron can be emitted from the surface, and then the ground state is the relaxed state where the electron is relaxed. So if you have an electron on the first state and it jumped from the first state to the ground state, it loses the energy, and it loses the energy in terms of the photon. And that photon has the energy that they're saying in the formula in the problem. It is 6 electron volts. And I know the photons have energy of the constant of the Planck's constant times the frequency. And they ask you to find the wavelength of this photon. So I can replace the frequency with h, and instead of the frequency I have the speed of light divided by the wavelength, and I'm looking for the wavelength. So from here I can find that the wavelength is going to be equal to the Planck's constant times the speed of light divided by the energy. And then the Planck's constant has to be staying in electron volts because energy is given in electron volts. So that is 414 10 to the negative 15, and then speed of light is 310 to the 8, and all of that divided by 6. So the wavelength of this photon is going to be equal to 207 nanometers. In this next problem, they say a sodium surface is illuminated with the light of the wavelength. So they give you the wavelength of this light, and so that I can figure out the energy of the photon. The work function of the sodium is given, so I have the work function of the sodium, so that's how much energy is needed to pull out the electrons from that sodium. And then calculate the energy of each photon in electron volts. So since the wavelength is given, I can calculate the energy of the photon. So for the first part, I have the energy of the photon is equal to the Planck's constant times the frequency. They ask electron volts, so I'm going to plug in 414, 10 to the negative 15, then times the frequency. The frequency I have to replace with the speed over the wavelength because they give me the wavelength. So I have the speed of light, 310 to the 8, and divided by the wavelength, which is 0.3 micro, which is 10 to the negative 6. So if I calculate that, I will get that the energy of the photon in electron volts is equal to 414 electron volts. 414 electron volts. For the second part, they ask you to find the maximum kinetic energy of the ejected electrons. So I know the energy of the incoming photons. So the photons coming in, and they have this much energy. And then these photons will emit the electrons with some kinetic energy. And that's the kinetic energy they're asking me to find. The energy that is coming is 414 electron volts. The energy that you need to pull out the electron, they give you is 246. So you have to spend 246 electron volt just to pull out the electron. so you have 414, you're spending 246. So the kinetic energy is going to be equal to the energy you had, which is 414 electron volts, minus the energy you will spend to pull out the electron. So the final kinetic energy, or the maximum kinetic energy of the electrons emitted from the surface of this sodium is going to be equal to 168 electron volts. So for the next part, they ask you to find the cutoff wavelength of the sodium. When they say cutoff length, they mean the wavelength needed to pull out the electrons from the sodium. So it's like the sodium has the cutoff wavelength that needed to pull out the electrons. So to find it, you have the energy of the, we can write the work function. So that's the work function, right? So this would be the work function, and the work function is equal to 246 electron volts, and that is equal to, again, it's the energy, so that's the Planck's constant, and then I can write, instead of the frequency, I can write the speed of light over the wavelength, and here I can find the wavelength needed to pull out those electrons. So the wavelength is going to be equal to the Planck's constant times the speed of light divided by the work function. So divided by the work function. And that will be equal to, I have to keep everything in Planck's constant electron volts. So I have 414 10 to the negative 15 times the speed of light, which is 310 to the 8. And all of that divided by the work function, or the work energy needed to pull out the electron, which is 246 electron volts, and that will give me the wavelength of the cutoff wavelength for the sodium equal to 505 nanometers. For this next question, they say, what is the minimum frequency light will eject photons from a copper surface? So they give you copper surface. Again, there is a work function or cutoff frequency for a wavelength for a copper surface, and then if this frequency is tripled, find the maximum kinetic energy of the resulting photoelectrons. Not be able to solve this question unless you know the cutoff work energy for copper. So for copper, I have 4.7. So the work function for copper will be 4.7 electron volts. The question comes from your book, so the book has the table where you look it up. So I looked it up for you. So the work function for copper is 4.7 electron volts. And I want to calculate the minimum frequency of the light that will eject from the of the photons ejected from the copper surface. I have the energy or the work function is equal to the Planck's constant, and then I have the frequency. And again, my energy is in electron volts, so I'm going to plug in electron volt Planck's constant. So I have 4.7 electron volt is equal to 414 10 to the negative 15 electron volts times the frequency. And so this frequency is going to be equal to 4.7 divided by 414 10 to the negative 15, and that will give me 1.135 10 to the 15 hertz. And then they say, if the frequency was tripled, what would happen to the maximum kinetic energy of the electrons? So I'm going to calculate the frequency, the energy of the photons if the frequency is tripled. So that will be equal to the Planck's constant times the frequency that I found, but now it's going to be 3 times as big. So I have 414 10 to the negative 15, and then I have the frequency that I just found, 113 10 to the 15, and times 3. So that's how much energy the photons will have if they have the frequency 3 times as large. So the energy that the photons would have equals to, it's the same as multiplying this number by 3. So that would be equal to 14.1. So that energy is equal to, in electron volts, that energy is equal to the work function plus the kinetic energy. And they give me the work function. This is the work function for the copper. So I have 14.1 electron volts is equal to 4.7 electron volts plus the maximum kinetic energy of those ejected electrons. So I have the kinetic energy of those ejected electrons maximum is equal to the difference between these two numbers, which is 9.4 electron volts. And again, if you have to convert electron volts into joules, you replace the electron with 1.610 to the negative 19, the charge of the electron, and your answer is going to be in joules. In this question, they say medical X-ray machines typically operate at potential difference. So they give you the potential difference here. Calculate the minimum wavelength their X-ray tubes produce when electrons are accelerated through this potential difference. So the potential difference, the voltage, is equal to the work done per charge. And in this case, it's going to be the energy per electron. And they ask you to calculate the wavelength. So if I calculate for the energy, I have the energy is equal to the voltage times the charge of the electron. And they ask you for the wavelength, and that is equal to h times the frequency, which is h, and I have the speed of light over the wavelength. So I can say voltage times the charge of the electron is equal to that. So the voltage times the charge of the electron is equal to Planck's constant, and then you have the speed of light over the wavelength. So the wavelength is going to be equal to the Planck's constant, speed of light, and then we have the potential difference and the charge of the electron. So now I can plug in my numbers, and I have the wavelength is equal to, and because I cannot cancel the electron volts in this case, I have to plug in my Planck's constant in not electron volts but in joules times seconds. So that will be equal to 663 10 to the negative 34 Planck's constant times the speed of light 310 to the 8. Then we have the potential difference is 10 to the 5th. And then the charge of the electron is 1.610 to the negative 19. So if I do these calculations, I'll get 12.43 10 to the negative 12 meters. It's the same as 12.43 picometers. In this question, they say what potential difference would be necessary to produce gamma rays with wavelengths of 10 to the negative 15 meters. And this wavelength is about the same size as the diameter of the proton. And potential difference, the voltage, is equal to the work done per charge. And the work is the Planck's constant, and then you can have the frequency over the charge. And they ask you what potential difference would be necessary to produce gamma rays, and the wavelength is given. So I have to convert the frequency into gamma and the wavelength. So I need to convert it with a wavelength expression. So I have the speed of light over the wavelength and divided by the charge. So if we plug in the numbers, we have the potential difference is equal to, again, my Planck's constant has to stay in joules times seconds because in this formula, I don't have any electron volts to cancel it with. So I have 663 10 to the negative 34 times the speed of light, which is 310 to the 8. And all of that divided by the wavelength, which is 110 to the negative 15. So that's 10 to the negative 15. and then the charge of the electron is 1.6 10 to the negative 19. And that will be equal to 12.43 10 to the 8 volts. And I think this is going to be our last question for this video, and it's ask you to estimate how many visible light photons a 20-watt light bulb with a wavelength of 500 nanometers emits per second, and the bulb is a typical efficiency, which is 3%. That means 97% of the energy goes into heat. So the power, that means that the power is only 3 joules per second, because 3% is only gonna be the ones that used. They say 100 watt light bulb, so you cannot use 100% of the light bulb. Not 100% of the watts will go into the light. Only 3% of it gonna go to the light bulb energy per second. So you have the power is not 100 watt, it's only 3 out of 100, 3%. So the power is given. In other words, you have the energy that is emitted. The energy is equal to 3 joules each second. So this energy is the energy of all the photons. So that means this energy is number of all the photons times the Planck's constant. The energy of one photon would be Planck's constant times the frequency, and that is all the photons. That gives you 3 joules of energy. So that I can rewrite as n, the number of photons, each carrying this much energy. So I'm going to replace it with a wavelength because they give me the wavelength. So they ask you for the number. So the number is going to be equal to the energy, like 3 joules, times the wavelength, the one that they give you, and divided by the Planck's constant, and times the speed of light. Again, in this case, I have energy in joules, so my Planck's constant has to be in joules per times seconds. So I have the energy, which is 3 joules, times the wavelength, which is 500 nanometers, so 10 to the negative 9. And then all of that divided by the Planck's constant, which is 663, 10 to the negative 34, times the speed of light, which is 310 to the 8. And if I do my calculations, I will get that n is equal to, so it equals to 75.4 10 to the 17 photons. That is all for the second video on quantum studies in our AP Physics 2, and I will see you in the third one. Thank you for watching this one.